Hi, so this is my video for SAT3 on the Riemann hypothesis. So firstly, to understand the Riemann hypothesis, we first need to understand the zeta function, which it's based off. And the zeta function is simply an infinite sum from n equals 1 to infinity, where each term is 1 over n to the power s. And s can be any number you choose. So the general form is 1 over n to the power s, but you can have s equals 1, for example, which then gives the infinite sum of n equals 1 to infinity of 1 over n to the 1. That gives you the series shown below with 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And that is clearly a divergent series. And you can have s equals 2 or zeta of 2, and you get the infinite sum of the reciprocals of the square numbers. So like 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. And that's shown to be convergent, and that converges to pi squared over 16. So whether the zeta function diverges or converges, and what it converges to if it does, is key to the Riemann hypothesis. We know that for all values greater than 1, the zeta function converges nicely to some number. However, if we try to use an s less than 1, for example, s equals -1, we can see that the infinite sum clearly doesn't make much sense anymore, as s equals -1 gives the infinite sum of the natural numbers 1 plus 2 plus 3 plus 4 and so on, which is clearly divergent again. So values of less than 1, of s less than 1, the zeta function needs to be defined in some other way, which we'll see later. So the zeta function can be extended to have s as any complex number now, with a real and imaginary part where s is equal to x plus yi, and x is of course the real part of s and y is the imaginary part of s. And when we extend the zeta function to have values of s with complex numbers, it maintains the properties which we saw before. So now for any value of s with a real part greater than 1, that'll still converge nicely to some value, which will now be a complex number. And it also means that when we have the real part of s less than 1, it will still be undefined and it won't converge nicely to any number, so we can't define it still for real values less than 1. So the example there given is s equals 3 plus 2i, zeta of 3 plus 2i, and that gives the infinite sum there, and that equals approximately to 0.97 minus 0.14i. So in order to define the zeta function beyond the domain where the real part is greater than 1, we need to use analytic continuation to define the function beyond that domain. So we've seen that the zeta function is only well defined when we have the real part of s greater than 1. To define the zeta function beyond that domain where the real part of s is less than 1, we can use analytic continuation. An analytic continuation essentially means that we continue the graph of the function beyond the original domain in a way that the function remains analytic. That is, it has a derivative everywhere still. And when you have this requirement that the continuation must remain analytic, it turns out that there's only one such continuation that works and that makes sense. And because there is only one such analytic continuation, we can now define the zeta function for values of s with real part less than 1. And that's shown below that the zeta function is now defined in two parts, the original infinite sum with the real part is greater than 1, sorry, and then this new function, this continuation where the real part is less than 1. Because we now have a well-defined function for all values of s, we can start analyzing the outputs of this function. The most important output is finding when the function is equal to 0. It's been found that every even negative number gives this output of 0. So for all values of s, where s equals minus 2n, these are called trivial zeros. Now, we know that for the real part of s greater than 1, that the series converges to some complex number. And we also know that from the analytic continuation that this is the same for values of the real part of s less than 1, except for when s equals minus 2n, as they give trivial zeros as an output. They still converge, but all those values of s equals negative 2n converges to 0, and they're the trivial zeros we saw just before. What we're not exactly sure about is in the domain where the real part of s is between 0 and 1. And it's been proven that all the non-trivial zeros must exist somewhere in this domain, but we're not exactly sure where. And so this domain is known as the critical strip. Now, the Riemann hypothesis says that all the non-trivial zeros, which we know are in this strip, are on a single line, and that line is where the real part of s is equal to exactly 1/2, as sort of shown in the diagram on the right there. And that line where the real part of s is a half is called the critical line. We know that there are infinitely many zeros on the critical line, but we basically are unable to prove that all the zeros are on that line and there is not zeros somewhere else in the critical strip, and that is the basis of the Riemann hypothesis. But the hypothesis is believed to be true, and many other mathematical results rely on this hypothesis, but as I said, it's yet to be rigorously proven. So the Riemann hypothesis and the zeta function itself encodes a lot of information about the distribution of prime numbers, and this is partly why it's so important. And one of the connections between the zeta function and prime numbers was discovered by Euler when he discovered the zeta function was equal to an infinite product, which he found involving the prime numbers, as shown there. And if the Riemann hypothesis were to be solved, then we'd also prove thousands of other mathematical results, and we would have a far greater understanding of the distribution of prime numbers and prime numbers in general, which is why this hypothesis is so important. So yeah, that's it. Thanks.